Today's session is about number system in the topics related to mathematics grade 9 CBSE syllabus. So let's see what number system deals with. Many a times in mathematics we have dealt with different types of numbers, the number line. So these types of numbers which are dealt, like the decimals, like the fractions, or the numbers in the power form, have got different types of classifications in mathematics, which we are going to discuss in brief in today's session of number system. So let's see the different types of numbers classified in the branch of mathematics. Coming with natural numbers. What are natural numbers? Natural numbers are the numbers which cannot be expressed in fraction form other than the denominator being 1. Say for example, I take the natural numbers to be starting from 1, 2, 3, 4, 5, so on and so forth. The reason being that it cannot be expressed in a fraction form but can be expressed on the whole with denominator as 1. Say for example, I can write this as 1 by 1 and this as 2 by 1, this as 3 by 1, and etc. So natural numbers cannot be expressed in fraction form other than with denominator being 1. And the numbers which are positive and start with 1. So 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth till infinity are called natural numbers. And usually the natural numbers are denoted by capital N. Capital N equals 1, 2, 3, 4, 5, 6 is the set of natural numbers. We write this as set of natural numbers denoted by capital letter N is what we call natural numbers in mathematics. Let's see how we can deal with different examples and understand natural numbers more better. Let's try with different types of examples. For example, I would like to test if the number 5.9 is a natural number. So my question is 5.9 a natural number? Now let's see the answer for this question using the basic definition as we have learnt in the previous session of natural numbers. Now 5.9, if I take this right down here, I understand that it is a decimal number to the approximation of one decimal place, and this in turn can be written in the non-decimal form as 59/10. So 5.9 indirectly can be written as 59/10, which breaks the rule of a natural number because the natural numbers accept only the denominator as 1. Other than 1, any other number we take cannot be accepted in natural number. Therefore, this not being equal to 1 is not a natural number, strictly by the definition as we have learnt. So 5.9 is not a natural number. And I write this as 5.9 does not belong to the set of natural numbers, is how we understand identifying a natural number or not a natural number. Let's see many other examples to understand the concept more better. Now let's see the other types of examples to understand the natural numbers more better. For example, my next question out here is root 9 a natural number? Now the question here is, all the numericals which are expressed in the form of roots cannot be a natural number because it is not directly in the numerical form, is point number 1, which I identify in the stage 1 of this being a natural number. Secondly, let's see if I can further simplify this to get a more simplified answer. We clearly know that 9 is a perfect square, so that root 9 we all know is equal to 3. Root 4 is 2, root 16 is 4, root 25 is 5, and hence root 9 is 3. Now, because this can be indirectly expressed in the form 3, we understand that root 9 is equal to 3, and clearly 3 is a natural number. And therefore, indirectly root 9, which can be expressed as equal to 3 after its simplified form, is a natural number, belongs to n, is how I understand the unsimplified questions given to be identified to be a natural number or not a natural number. So what do we understand from this basic example is that whenever a question is given about testing on a natural number or not a natural number, we try to simplify it to the most simplified form. It is very important to note that until and unless a given problem is simplified to the most simplified form, we cannot judge on the number being a natural number or not a natural number. Let's do one more example. Is 5 cubed a natural number? This is my question. Yes, let's see. Or let me add this to it. Now, is 5 cubed by 25 a natural number? So the first thing what I do is I try to reduce this to the most simplified form, and then I get to identify on the final justification of whether this number is a natural number or not a natural number. So let me take the given problem 5 cubed by 25, and let me try to simplify this more further and then justify on this natural number concept. Now we know that 5 cubed is 5 times 5 times 5, and 25 can be written as 5 times 5, and then the two 5's get cancelled out here. Then finally I am left with only one number, which is 5. And that clearly makes me understand that the given question 5 cubed by 25 is nothing but indirectly the simplified form of 5. And then this we all know belongs to natural number. Therefore, 5 cubed by 25 is a natural number, is how we justify through the most simplified form and then justification through that. Next, let's go with another example to understand the natural numbers more better. Now the question here is root 49 plus root 4 by root 9 a natural number? So here we see that there is more part of which to be simplified before we justify on this given number being a natural number or not a natural number. So the given question being root 49 plus root 4 by root 9 is to be further simplified, as we clearly know that root 49 is 7 and root 4 is 2 and root 9 is 3. I reduce them into the non-root form by using the perfect square number concept. And using this, I clearly understand that 7 plus 2 can be added further to get 9, and the denominator is 3. So that this can be further simplified, as we know that denominator and the numerator get cancelled for 3 times in the numerator. So 3 1s, 3 3s. My final answer is 3 for the given problem. So the most simplified answer for this is 3, and which is clearly a natural number. Therefore, the given number is a natural number. Therefore, root 49 plus root 4 by root 9 is 3, which is clearly a natural number, belongs to the set of natural numbers, capital N. The next set of numbers in the branch of mathematics is the whole numbers, continued from the set of natural numbers. So what are whole numbers? So let's discuss about whole numbers in this section. Whole numbers are the numbers which start from 0. It's very simple because every natural number along with a 0 is a whole number. Say for example, I have my natural numbers revisited to be 1, 2, 3, 4, 5, 6, etc. up to infinity is what we have discussed in the previous session. Then whole numbers is nothing but natural numbers, and including 0 is what we identify the difference between natural numbers and whole numbers. So with this we understand that the set of whole numbers is 0, 1, 2, 3, 4, 5, with the only additional difference being 0 between the natural numbers and the whole numbers. 0 along with a natural number is a whole number, is how we identify through the words. Zero along with natural numbers is a set of whole numbers, and this is denoted always by capital W. 0 along with natural numbers is a set of whole numbers denoted by capital W. Let's do some example problems to understand the concept of whole numbers more better. Now that we have understood about the whole numbers and the difference of whole numbers as compared to the set of natural numbers, let's try with some example problems to understand the concept more stronger. For example, I have is (7.1) a whole number? Is my question. 7.1, let's try to see if it can be expressed as a whole number. So I take the number 7.1 out here, and this, when I express it in a non-decimal form, can be expressed in the form 71 over 10. So 7.1, the decimal form, is expressed in the non-decimal form 71 over 10, and this clearly states that because the denominator is not 1, and as we have discussed about the natural numbers and the whole numbers being all natural numbers including 0, this cannot be a whole number. It is instead not a natural number too. Therefore, 7.1, which is expressed in the fraction form, cannot be a natural number, and equally this also cannot be a whole number, is how we understand the concept of whole numbers. Now let's try to see some complex examples to understand the concept of whole numbers more stronger. For example, I have the question which says is root 32 minus 2 power 5 a whole number? Or I take this to be root 64 minus 2 cube a whole number, is the question I have put forth here. So for this, let's try to see the justification of this being a whole number or not a whole number by first trying to simplify the given number, because every number which is being justified demands for the most simplified form. So let's try to simplify further and then justify for this number being a whole number or not a whole number. The given question is root 64 minus 2 cube. As we know that root 64 is 8, because 8 square is 64 under root, which gives me 8. So root 64 is 8 minus 2 cube, which we know is 2 times and 2 times which further gives me 2 2's 4, 4 2's 8, and this finally simplifies to 8 minus 8, which is 0. Now I have the most simplified form of this to be 0. So 0 is a whole number, as we clearly know that the set of whole numbers start from 0, 1, 2, 3, etc. Therefore, this belongs to whole number, that is indirectly root 64 minus 2 cube is a whole number. Also, it is very important to note that this is not a natural number, but root 64 minus 2 cube is not a natural number, because we have clearly seen that n starts from 1, 2, 3, etc. and whole numbers start from 0, 1, 2, 3, etc. And therefore, this is where I have this belongs to W, but here it does not belong to n. 0 is part of whole numbers, but 0 is not part of natural numbers. Is how we understand the difference between set of whole numbers, capital W, and set of natural numbers, capital N. Integers. The next set of numbers in the field of mathematics after the natural numbers and the whole numbers is integers. And this plays one of the most important role in the set of numbers in the number system. So let's see what are integers or set of integers in the field of mathematics. Integers are denoted by capital Z or capital Z, and it is nothing but the set of all numbers, natural numbers and whole numbers, which are both positive and negative. So in the most simple understanding, I understand that the set of integers is the natural numbers and the whole numbers taken both in the positive side and the negative side. Say for example, let me start with the positive side. We know that the whole numbers are 0, 1, 2, 3, 4, 5, etc. up to infinity is what we understand the natural numbers or the whole numbers added with 0 in the positive side. So integers also include the negative part of it. Say for example, I have all the positive side on the right side, then I have all the negative numbers on the left. Minus 1, minus 2, is how we frame the complete set of integers in this form of the positive side being the natural numbers of the positive sign, and the left side being the negative numbers of the natural numbers which are negative in sign divided by 0. So I have all this to be positive natural numbers and all this to be negative natural numbers along with 0. So positive natural numbers plus 0 plus negative natural numbers together make the set of integers, is how we understand the difference between the natural numbers, the whole numbers and the integers, the set of integers being denoted by capital Z. Also, it is very important to note that the set of integers is again further classified into positive integers and negative integers and non-negative and non-positive integers. So let's see how the classifications are done. Say for example, I have the set of integers. Then I have 4 types of classifications for this. The first being positive integers denoted by Z plus. And next is negative integers denoted by Z minus. And thirdly, I have non-positive integers. And next I have non-negative integers. So this set of integers denoted by z, which has both the positive and negative signs and the neutral 0, is classified into 4 types, which is very essential to understand before we understand the entire set of integers z. So this is classified into positive integers denoted by z plus, negative integers denoted by z minus, and non-positive integers and non-negative integers. So let's see what each of them differs with. Z plus, as clearly mentioned for positive integers, states that we pick only the positive part of the integers. So we know that the positive integers start from 1, 2, 3, 4, 5, etc. Therefore, this set Z plus has all the numbers which start from 1 and end till infinity. So set of positive integers denoted by Z plus is now 1, 2, 3, 4, 5. Similarly, the negative integers Z minus is all the numbers which come on the negative side, that is on the left of 0 of the main set of integers Z. Therefore, negative integers denoted by Z minus starts with -1, -2, -3, so on and so forth, is how we write the set of negative integers. Similarly, let's see what does this non-positive and non-negative integers differ with their definitions as compared to these. It is very important to note that both look similar, positive and non-positive. So let's see how the difference comes. So positive integers is 1, 2, 3, 4, 5, and non-positive integers is all those integers which are not positive. Now, before we come into classification of non-positive and non-negative integers, let's try to make a very important note that 0 is neither positive nor negative. It is neutral, neither positive nor negative. It is neutral, is how I understand the importance of 0 in the branch of numerals. So 0 is neither positive nor negative. It is neutral. Therefore, when I say non-positive, I include all the non-positive integers which are neither positive but only negative, but even 0 included, because even 0 is a non-positive integer. So it comes out to be 0, -1, -2, -3, and so on and so forth till infinity. Now we have the non-positive integers to be 0, -1, -2, -3, so on and so forth. As compared to the negative integers, we clearly understand that non-positive integers is nothing but the set of negative integers including 0, because 0 is a non-positive integer, neither positive nor negative. And therefore, I have this indirectly written as all the negative integers including 0 is how I understand the non-positive integers. Similarly, let's see what does the non-negative integers define. As we clearly know that non-negative indicates all the positive numbers, so I have all the positive natural numbers which come under the branch of non-negative integers and including 0. Therefore, if I have this set which includes 0, which is neither positive nor negative, and including 1, 2, 3, 4, etc. till infinity, then this set is non-negative integer set. So set of all non-negative integers being this is clearly understood as all the positive integers including 0. Therefore, as we have written for all negative integers including 0, now as we have this non-negative integers, we have this to be z plus union 0. the set of all positive integers including 0, which is neither positive nor a non-negative integer, is the set of non-negative integers which is combination of positive integers and the 0. Therefore, I have 4 classifications for z, which has positive integers denoted by z plus, which has 1, 2, 3, 4, 5 till infinity, and the negative integers denoted by z minus includes -1, -2, -3, so on and so forth. And non-positive integers, which is all the negative integers including 0 denoted by z minus union 0, and similarly the non-negative integers, which includes all the positive integers and the 0, is how we understand the different classifications of the set of integers z. Now let's see some example problems to understand the concept more better. Let's see the relation between n, w and z before we go through different examples to justify the set of integers and its identification in the respective manner. So as we have seen, the set of integers denoted by z is all the negative integers, which is -3, -2, -1, and 0, 1, 2, 3, 4, 5, etc. is how we get the set of integers z. Let me also take into consideration the set of natural numbers and the whole numbers. As discussed in the previous session, the set of natural numbers n is 1, 2, 3, 4, 5, and so on, and the set of whole numbers denoted by capital W is 0, 1, 2, 3, 4, 5, and so on and so forth till infinity. Now let's see what is the relation between z, n and w. As we clearly see, let's start from w and then with n and then with z and make a relation between w, n and z. I clearly see that w is all natural numbers including 0. So I can write this as n union the element 0, singleton 0. And I see the relation between z and w to be all the negative integers, as seen, the first half being the negative integers and the right half being the positive integers divided by the neutral 0. So I can write this as z minus union 0 union z plus is what we get. Now set of integers is the union of set of negative integers union singleton 0 and union the set of positive integers. Now with this, I clearly see that the set of natural numbers is nothing but the set of positive integers, because we clearly see the natural numbers matching with z plus, as z plus is 1, 2, 3, 4, 5, and the set of natural numbers is also 1, 2, 3, 4, 5, etc. So z plus is n and z minus is set of all negative integers. So I see z minus is minus n is how we understand the relation between z minus and n, is how we get the different types of relations between z, n and w. Let's see some example problems to understand the set of integers, set of natural numbers and set of whole numbers combined, and understand the identification of a number in each of its classification, either as a whole number or as a natural number or as an integer. To start with an example, my question here is minus 5 by 2 an integer? So the question here is minus 5 by 2 an integer? So let's try to identify the classification of this given number using the concept of the integer or a natural number or a whole number. Now clearly minus 5 by 2 is in the fraction form, which cannot have the denominator as 1, but other than 1 it is 2. and therefore this can be expressed only as a decimal form but cannot be expressed as a non-decimal form with the denominator 1, and therefore this is clearly not an integer, or it is not a natural number or a whole number. So therefore the outcome is minus 5 by 2 is not an integer, is not a natural number, is not a whole number, because we don't have this in the denominator with 1. Let's try to identify with a different example. So for example, I have, is 2 minus 5 cube a natural number, or a whole number, or an integer? So let's try to identify the answer for this question using the properties what we have learnt. Now coming to this, the given problem is 2 minus 5 cube, and I have to justify for this number being an n, a w, or a z. So for this, we come with the rule that I simplify this to the most simplified form. And therefore, this when simplified to the most simplified form, I get this to be 2 minus 5 cube, which is 5 times 5 times 5. And this comes out to be 2 minus 125, because 5 times 5 is 25 and 25 times 5 is 125. This on further simplification gives minus 123, negative 123 is the final simplified answer for this. Now with this, I clearly understand that this is not a natural number, though it can be expressed with the denominator as 1, and a non-decimal number being expressed with the denominator as 1. But this is an integer, because an integer has the negative natural numbers and the positive natural numbers, including the neutral 0. Therefore, I understand that 2 minus 5 cube, which is indirectly expressed in the form minus 123, is not a natural number, is not a whole number, but is an integer, because it is accepted in the set Z. Is how we understand the different classification of the numbers justified through n, justified through w, and justified through z. Now let's try to see the next set of numbers in the number system, rational numbers. What are rational numbers? Now that we have passed through the phase of integers and the natural numbers and the whole numbers, let's try to enter into the concept of rational numbers. But before we discuss its brief introduction, let me just make it very clear that the set of all NWZ form a different branch in the number system. This forms a special branch in the number system because this accepts fractions and decimals, whereas N, W, and Z do not accept the fractions or the decimal representations. So let's see in brief the definition of a rational number. A rational number is denoted by capital Q, and it is defined in the set form as all the numbers which can be written in the form P by Q such that P and Q are integers, the condition being that the numerator and the denominator must be integers in the fraction form P by Q, and most importantly, the Q should not be equal to 0. The denominator should not be equal to 0 is how we understand the set of rational numbers. So whenever we think of rational numbers, we think of this common formula Q, which stands for the set of rational numbers. Let's see more in brief on how we define a number to be a rational number based on this set notation. Let's try with an example problem. For example, I have 7 over 3 and I wanted to just justify on whether this number is a rational number or not a rational number. So clearly I try to classify initially in the form P by Q, where my P is 7 and my Q is 3. So I pick the P, which is 7, and I pick the Q. So P is equal to 7 and Q is equal to 3 are just justified through these two conditions. Now clearly I see that P and Q must be integers for the number written in the P by Q form to be a rational number. So this acts as the rule 1 and this acts as the rule 2 to identify for a number to be a rational number. Rule 1 clearly states my P is 7 and Q is 3. In this example problem 7 over 3, and clearly P and Q, which are 7 and 3, are integers, which we have discussed in the previous session. So therefore P and Q are integers is the first test which this passes out here. Secondly, the rule 2 being Q. So let's see what is Q here. Q is 3, and we know that the number 3 can never be equal to 0, and therefore Q is not equal to 0, and this number also passes the test number 2. So with the passing of the two tests, this and this, I can proudly say that 7 over 3 is a rational number, belongs to Q because it passes through test 1 and test 2. Test 1 and test 2, and therefore 7 over 3 is a rational number. Let's try with one more example problem. Say for example, I have the question is (4 by root 3) a rational number. So in order that I identify for this to be a rational number, I have to pass through the two tests, test 1 and test 2. So coming to the number, let me pick the number which is 4 over root 3 and identify each of P and Q from the given number. So clearly I see my P is 4 and Q is root 3. So here my P is 4 and Q is root 3. Now let's try to go through the test number 1. The test number 1 where I have to see that both are integers. Now as clearly I see P is equal to 4 is an integer because its denominator is 1, but I see that Q is equal to root 3 cannot be a numeral which can be expressed in the denominator with 1. This being a root which cannot be further simplified clearly says that this cannot be an integer. Therefore, here P belongs to Z, but Q does not belong to Z, and therefore it fails with test number 1, indirectly saying that this number cannot be a rational number because this fails through test 1, P and Q being integers. Therefore, does not belong to a rational number. It belongs to Q. Let's take one abnormal example through which we understand the rational numbers. Now my question here is 5 by 0 a rational number? So let's see how we can justify this through the test number 1 and the test number 2. Now clearly I see that the number 5 over 0 in the given question should be classified into P and Q, where I identify the P being the numerator, which is 5, and the Q being the denominator, which is 0, as compared to the given set. Now clearly, going through the test number 1, I see that the P and Q are integers, which is an essential factor in test 1. Next, I identify the number Q, which is 0, and this also belongs to Z. So it definitely passes the test number 1, where P is 5, which belongs to Z, and Q is 0, which belongs to Z. Now let's see the test number 2, which also needs to be passed before we justify 5 by 0 to be a rational number or not a rational number. So coming to P and Q, the test number 2 which says Q should not be equal to 0, but I clearly have Q equal to 0, and therefore this fails through the test number 2. This fails test number 2, and therefore it cannot be a rational number. Therefore 5/0 or any number denoted with the denominator being 0 cannot be a rational number, because 1/0 is undefined, which is infinity. It's how we understand the property. And therefore 5/0 is undefined, which tends to infinity, and it is not a rational number. Decided through the test number 1 and test number 2. Now let's take an example of a fraction which involves the roots to understand the rational numbers more deeply. For example, I have a number √4/√9, which I have to decide on this being a rational number or not a rational number. So my question here is √4/√9 a rational number? So let's justify this given problem through the test number 1 and the test number 2 before we decide for the number being a rational number. Now the given question is √4/√9, which can be further simplified. As we have discussed even in the previous sessions, a number needs to be completely simplified before we justify for that number being a rational number or a natural number or a whole number or an integer or any other number in the branch of mathematics. So let's try to simplify this further, where √4 clearly can be written as 2, because 2 square is 4 and √9 is 3, 3 square being 9. So the simplified form of √4/√9 is 2/3, which now cannot be simplified further. So therefore I put this number 2/3 indirectly to both the tests, test number 1 and test number 2. Therefore here I get my P as 2 and my Q as 3, where in order to make the test number 1, I clearly see that P is equal to 2 is an integer and Q is equal to 3 is an integer. Therefore both P and Q pass the test number 1. Now let's try to see the test number 2. Clearly the test number 2 is about picking Q, where I got my value of Q, which is 3, and more further 3 is a non-zero number. Therefore this can never be equal to 0, and therefore equally Q equal to 3, which is not equal to 0, also is the pass of the test number 2 by the number √4/√9. So this number, when simplified to 2/3, passes the test number 1 and also passes the test number 2, which makes us understand clearly that because of the two tests being passed, this number √4/√9 is a rational number, and its simplified form being 2/3. So any number expressed in root or a non-root or a decimal or a non-decimal is justified through its most simplified form. The most simplified form here being 2/3, which is a rational number. Next, let's take an example of a decimal number and justify on whether the given number is a rational number or not a rational number. For example, I have is 4.956, which is a number which is expressed in decimal form up to 3 decimal places, and I want to justify this for a rational number. So my question here is 4.956 a rational number? Let's try to see based on the two tests applied for this basic definition. The given question is 4.956, and let's see if this can be expressed in the form P by Q, satisfying these two properties. Now, when I take the more simplified form, I clearly understand that any decimal to be tested for a rational number should be expressed in the non-decimal form, or should be converted into the non-decimal form. Therefore, 4.956, when it converts to the non-decimal place, it has its 3 zeros, which makes added to the denominator, so that this decimal 4.956 can be expressed as 4956 by 1000, the 3 zeros being counted on 1, 2, and 3 decimal places. Therefore, this, which can be expressed as 4956 by 1000, is the indirect simplified form of the given decimal 4.956. Now, let's see if this passes through the two tests for a rational number. This is P, this is Q, and I have my P as 4956, and I have my Q, which is 1000, on the denominator. Test number 1, P and Q must be integers. Clearly, 4956 is an integer and 1000 is an integer. So I have my P and Q, which are integers. Therefore, the test number 1 is a pass. Next, coming to the test number 2, I have my Q, which is 1000, and which is not equal to 0, because 1000 can never be equal to 0, and therefore this also is a test number 2, which is a pass. Therefore, this number satisfies test 1 and test 2, thus this number being a rational number. Therefore, 4.956, which is the indirect representation of 4956 by 1000, must be a rational number Q. Is how we understand the concept of rational number, understood through the two tests applied for the given problem. Now that we have understood about the rational numbers, let's try to see the relation of the set of rational numbers Q with natural numbers, whole numbers, and integers. The relation says we have our natural numbers 1, 2, 3, 4, etc., and whole numbers, which is 0, 1, 2, 3, etc., and my set of integers, which is negative on this, and my rational numbers, which is all in the form P by Q, such that PQ belong to Z and Q not equal to 0. So clearly I understand that every natural number is a rational number, because if I take a number 7, which is a natural number, I can equally write this 7 as 7 over 1, which passes through the two tests. That is, this being P and this being Q, my P is 7 and Q is 7, Q is 1, and both belong, 7 and 1 belong to Z, set of integers, and therefore it passes the test number 1 for Q, and 1, which is the denominator, is not equal to 0. Therefore, every natural number 7 belonging to n can also be expressed in P by Q form, that is 7 by 1, and it becomes a rational number. Therefore, 7 belongs to n and 7 also belongs to Q. Therefore, I can say all natural numbers are part of the rational numbers. All integers are the part of rational numbers, and all whole numbers are part of the rational numbers. Is how we understand the concept of natural numbers, whole numbers, integers, and Q. Is how we get the relation between n, w, z, and Q, these three being part of Q. Q is bigger than n, w, and z.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.